Good morning, good day, good afternoon. Welcome to our webinar today, which is going to be about reflective absolute encoders. And we will have two presenters here, Goran Pancha and Silvan. And we will start momentarily, but before we start, I will just take you through the webinar tool. So if you follow this presentation, you have the control panel. You can click on the control panel on the arrow here to expand it. And then there's a section for a question where you can ask questions which we will answer after the presentation. We will encourage you to ask questions, and we will do our best to try and respond to them during the given time. If there are more questions, we will follow up with you directly and provide you with answers to your questions. You have the screens here. So you have the top side here is the speaker, and then you have a presentation screen. And in the middle, you have a scroll function where you can size up and down and decide which picture you want to see. So you have the speaker side and the presentation side. And during the demonstrations, the presentation will not be shown, so you will see the full screen of the video. So with that said, I would like to pass on the word to Mr. Goran Pancha to start the presentation.
Thank you, and hello and welcome to our live webinar of reflective optical encoders. My name is Goran Pancha, and I'm responsible for the optical reflective encoder ICs. And before we start and present our live demonstration, let me give you some basic facts and some basic figures about iC-PZ. So today we will talk about, of course, the iC-PZ in package OQFN 5x5 with 32 pins. We will show you and demonstrate an encoder disk of 69mm outer diameter, and we will present you a linear stage equipped with a linear scale of 160mm with a native resolution of 204.8 micron. So when we talk about optical reflective encoder ICs, you can see the basic principle here on the right side. It's here drawn in a cross-section. You can see here the PZ sensor with the LED in the center of the package. On the left and right side, we have the incremental and absolute encoder windows, which detects the reflection of the code of the disk or linear scale. On the left side, you see a picture, or a live picture. You will see later on the real stage or the real drive with the 69mm equipped with the PZ1M board and the iC-PZ 205, and the 69mm with the code disk with 1024 native incremental tracks. So when we talk about unique features or special features of iC-PZ, and one of them is what we call the flex code. The flex code is a feature which allows you to cover almost any diameter starting from 60mm up to 45 with PZ2656, and with code disk sizes bigger than 45 and up to linear applications to 6.71 meter. You can use the iC-PZ 205, which will be presented in the live demonstrations later on. So special features and, of course, a huge flexibility gives the iC-PZ also for the assembly tolerances, which is mentioned here. As you can see, for a 26mm disk and the PZ 2646, we have a tangential displacement allowance of tolerances of 0.5mm plus minus. In radial displacement, we have 0.4. And typically, nominal error gap is 1.75 with a tolerance of plus minus 0.5mm. So this gives you a huge flexibility, especially for mechanics and tolerances of gearings and etc. Then we have what we call the signal conditioning on chip. That means that some imperfections that you have from tolerances, mechanics, and so on, which normally will be shown as an offset, differences in offset, in amplitude, and phase, is conditioned or leveled by the chip itself, so that you just have to put on or trigger these function and process by command. So there is no external software or external hardware needed. It's almost everything is done and conditioned on the chip. The same is for what we call the digital conditioning or digital adjust, which you'll see also later on in our demonstration. Some imperfections regarding the assembly of the code disk versus the sensor can be compensated and can be leveled by the chip itself. So one other excellent flex count feature is that when we look, for example, here on a code disk with 256 native incremental resolution, we can use the internal interpolation core of up to 14 bits, which allows you to set up all possible resolutions, even odd resolutions and odd numbers up to 22 bits. With an internal position update rate of 80 megahertz, we have very fast and short latencies down to 2 microseconds from the optical change of reflection to the output signal of the voltage of the pads on the output. The maximum frequency of AB, for example, is up to 6.5 megahertz. So for first tests and for first measurements in your lab, we recommend you to use our evaluation kit, which will be also shown in our live demonstration for the linear and the rotary stage. And this evaluation kit consists of a motherboard, which has or allows you to have all the access to the outputs in the interfaces of iC-PZ, connected with a flex cable to our PZ1M scanner module, which is soldered with the PZ205 or PZ2656. Then the evaluation kit comes with a code disk, a standard code disk of 26 millimeter, so that you are able to measure, test, and evaluate the first signals with our sensor. And of course, you can connect a BIS to PC adapter, which allows you to use our GUI software so that you are able to configure and set the parameters that is needed for your application. So let me summarize just quickly the unique and special features. So we have a small package, a standard OQFN 32 5x5, which can be soldered in a standard SMT process. We have a huge functionality of automatic signal adjustment on chip, including the LED power control that we have if there is some deviation in the air gap of the system. We also have, and this will be shown by my colleague later on, is runout compensation if there is some tolerance in eccentricity by applying the code disk on a shaft. We have these unique features like flex count, flex code, the huge assembly tolerances. There is also a huge temperature operating range or wide operating temperature range of -40 to 125 degrees. So that's from my side about the unique features and facts. And now I would like to hand over to Silvan Etle, who will show you some setup and for the rotary encoder of 65 millimeter.
All right, thanks Goran. This is Silvan, your sales and applications engineer, with a very warm welcome all around the globe. And in the next, let's say 20 minutes, I'd like to get very practical, very hands-on, and run you through setting up an encoder system from scratch with the iC-PZ 205 and our 69mm aluminum disc, the PZ05SM. So a quick note before, you're of course very invited to ask questions here, but for in-depth discussion, please feel free to reach out to Goran and me anytime, drop us an email, give us a call. We are very happy to talk to you. So, what this will be about. For those of you who had already the chance to set up an encoder with the iC-PZ series, you will probably be quite used to this procedure already. And for the new guys, this is pretty much the recommended setup procedure from our application node 1 and also from our application node 2 if you're using a FlexCode disk, which we will do here in this demonstration. So those are available for download from our website. And I don't want to give too much of an introduction here because I'm going through all of those steps in a minute, giving some hints here and there. So I do suggest we dive right into the application. So taking one step to the right, here's our hardware, our setup that I'd like to guide you through. And the first step you of course have to do is some kind of preparation. You will need hardware, software, and also some documentation. And for the hardware, we are providing, as Goran already introduced, the PZ1M evaluation board that is shown here. And the scanner module, the PZ205, is sitting on bottom of the PCBA here. And next to it, we do have our 69mm aluminum disc, the PZ05SM, that is sitting here. And via this ribbon cable, I've connected the PZ2D, which is our motherboard, that allows for somewhat easy signal inspection and also a very comfortable connecting of the components. And to the sub-D connector of the PZ2D, I've connected one of our base to USB adapters. I'm using the MB5U here, but you're of course free to use the MB4U or also MB3U, it doesn't matter. And then I'm going via USB into one of the USB ports of the computer. So after you're done with all the hardware, you will of course need some software, and actually one piece of software you can get for free from our website, which is our iC-PZ evaluation GUI software. I will show that in a minute. And besides, you'd like to have some kind of guideline, and we are providing application notes to get you into the system. I do very much recommend to start with application node 1, and if you're using a FlexCode system, take a look into application node 2. And besides, you will require the code disk description document. It's a very lean 2-pager document that contains all the parameter settings that you will need to set up the correct target. Because as Goran already mentioned, we do have a vast variety of targets that can be used with the iC-PZ series. What I'd like to emphasize here is that you do not necessarily need to have a look into the datasheet for setting up the system for the first time. Of course, if you're going into details, the datasheet is our reference. But for setting the system up, you're totally fine with the application node 1 and also application node 2. So that's it for the preparation step. And the next, or actually the first step in operation then, is telling the system which target you're using. And therefore, you should have a quite quick look on page 2 of the code disk description document. And there we do have a table that contains all the parameters and settings that those are required to set up the system correctly. So the system knows how to interpret the pseudo-random code into the correct absolute position. And for the disk we are using here, the 69mm disk, I've just made a screenshot. We do have the sys override that is corresponding to the native resolution of the system. So we are having a 10-bit system here with 1024 CPR. Then we have the parameter FCL, which is the length of the flex code, actually the same as the CPR. And then we have the FCS, which is kind of an identifier, so the system knows how to map the PRC to the absolute position. So let's keep all those three parameters in mind, and I'm going to the GUI and just entering them. So clicking here, as we do want to start from scratch, I'm starting the GUI. I do have a shortcut here, so it's going a bit faster. Okay, waiting. Here we are. This is our latest release, release C5. We've just done, I don't know, two weeks ago, I think. So this is our very latest release, and I'm pressing connect here. We are starting from an absolute default configuration. So this is what you will find when loading a default configuration. So there has no parameter settings done already. And what I'm doing now for the flex code settings is going to System Config tab. And first one is the chip system override that is shown here. And as I said, we are using a 10-bit native resolution disk. I'm opening the drop-down here and clicking 10-bit system. Then next, I'm going on bottom of that page, seeing the flex code section here. And here's the parameter FCL, flex code length. And as you can remember, we are entering 1024. And the identifier for that disk is 0, but for the sake of completeness, I'm entering this as well. So we are fine with the first step. Now we're ready for mechanical alignment, and I'd like to show you how to really make advantage of the huge assembly tolerances Goran already mentioned in the presentation previously. So yeah, I'd like to show that we really start from a mess of alignment, okay? So I'm first losing this screw here, and then really start from anywhere, okay? So there's no alignment going on whatsoever. And what I'd like to show you now, that there are two indicators that can be used very nicely to align the system. First one, when using the PZ1M, we do have the white alignment marks printed on top of the PCBA. So there's kind of a cross that really wants to be in the middle of the two code tracks. And the second one is the LED, is the blue LED. And as you know, we do have an integrated LED power control, and what is doing this is when there is no signal coming in from the code tracks, this will shine very, very bright blue. And I'd like to show this, and perhaps the cameraman could zoom in. This would be great. So I'm going out a little, and as you can see, hopefully see, the LED is driven quite high, as you can see. It's very shining bright blue. And if I'm going above the code disk and getting a signal, okay, the LED will be regulated. So this is a very good indicator to know, okay, if there's some signal on my photodiodes or not. And then I'm leaning over and try to find somewhat the right spot with the mixture of both indications I've just showed. So let's find this. Looks good. If I think this is set, I'm tightening the screws here, and we will see if this rough alignment by eye has done its job in the next step. Because what we can do now is make use of the digital adjustment to really see if our system is precisely aligned. And therefore, we do have two target values given in the code description document that tell you the ideal position of the code disk versus the sensor related to a 1.75 millimeter air gap. So we do have the AI scale, which is basically corresponding to the radial displacement. I'll show that in a second. So let's just keep 1.04 in mind for the AI scale. And the AI phase is actually related to the tangential displacement. Let's keep the 20 degrees in mind when doing this step. So therefore, I'm going to the Adjustment tab here. Going to Adjustment Digital. And then, as you can see, on the left side, we do have the AI scale. And on the right side, we do have the AI phase values. And what I'm doing for the precise mechanical alignment is enabling the dynamics. And I'm starting with a moderate dynamic for both. Okay, and then I click Read Continuously, the checkbox here, and start reading the parameters. And what I have to do now is spin the disk at like any speed. Okay, and what you will see, okay, I've hit very, very good already. Wow, I've never hit it that good during testing, I swear. Okay, so as you can see, the values are a bit changing, and this is due to the digital adjustment that I will explain later. Those are corrected during or in operation. And what I'd like to show now is when turning the X and Y manipulators of our demo stage here, how those parameters are related to the displacement. I'd like to start with the radial displacement. I really hit that quite nicely here already, but let me just show it. Okay, this is our Y manipulator in radial direction. So I'm going in any direction, and as you can see here for the AI scale, when turning the micrometer screw here, this is changing. So I'm going out now, going in again, turning the screw, and you get the relation from that parameter to the displacement here. So we wanted to hit 1.04. I've hit that already pretty good. Okay, but as you can see, the alignment goes like this with the Y manipulator. For the X manipulator or the tangential alignment on the right side, you can see that we are still a bit far away from the 20 degrees, which are our target value. And again, I'm turning the micrometer screw here, the manipulator, in Y direction, and as you can see, we're coming close to our 20-degree target value. And what you've done now is somewhat set up like a golden device to start with in the lab, because this is really close to an ideal position. Okay, when I've done so, we can stop reading here and we can disable the dynamics again for this step. So we're done with the alignment. I can check the air gap again. I've done this previously because don't want to spend too much time on the alignment here, but it looks good. We can use the Z manipulator to adapt this as well. So after doing all of the alignment, we are actually nearly ready to do the auto calibration features, to perform the auto calibration features. But therefore, we have to do a quick preparation step, which is changing the filter configuration. And we do have two filter modes integrated. One that is quite robust for starting with a system that is not yet adjusted in any way. And this is what we have to choose for the initial analog auto calibration. Pretty quick step. Going to the System Config tab here. Going to the Interpolator section on bottom, and it's already per default hex 6E, but I'd like to show this. We will need this later. I'm clicking the Before Analog Adjustment Filter parameter. And we are done with this step. Quite quick preparation step to get ready for the analog adjustment or auto calibration. And the analog auto calibration compensates for phase, offset, and amplitude of the analog signals so that the integrated 14-bit interpolator will be fed with best signal quality possible. And as Goran already said, I'd like to emphasize this again. There are no computations or calculations done in software. This is all done in the chip, so you just trigger it via command over the serial interface, for example, the BIS in this case, but also the SPI interface if you're using an MCU, for example. So quickly showing this. Again, going to the adjustment tab, and then going to the adjustment analog in this case. You can spin the disk at like any speed, and we have also integrated what you can see here on bottom, a low speed option. So this is really just if you can spin with a very few RPM. You can click this, but we do not need this for our setup here. And you can leave all the auto calibration settings that are shown here with the gray background on the left side. By default, that's totally fine. And what I'm doing now is just clicking the adjust button, and the software will just send one single command. There won't be any other communication, and all the auto calibration will be done inside the chip, and then afterwards the software will read the adjustment parameters. So I'm clicking this, and that goes pretty fast, and as you can see, we do have some offset adjustments here for the cosine and sine, and also some gain adjustment, very few just, and also the phase adjusted a little bit, quite a little bit. And what I can do now, just as a quick hint to see if my system is stable, I do a re-execution of that command and see if I'm having some variation of those adjustment parameters. So again, clicking this. Okay, no changes at all, so it seems pretty stable. Let's re-execute it again. Okay, perhaps you've seen it. Here was a quick jump, perhaps in the LSB. So this system seems to be very stable already, and we are done with the analog auto calibration. So before going ahead with the digital auto calibration, we again need to adapt the filter settings. And the second filter configuration that we are providing with the iC-PZ series will also be the one that you will be using in your final product. So again, same steps as before, going to the System Config tab, on bottom the interpolator section, and clicking here into the drop-down of filter parameter 1 and selecting after analog adjustment. So that's it. So now we are ready for the feature which, if you ask me, is the most impressive one about the iC-PZ series. So this is what we call digital auto calibration. And what it's doing is actually somewhat analyzing the position or the alignment between code disk and sensor, and compensating for a somewhat misalignment so that the system is actually working as in ideal position. So again, this is just done by triggering a command, very similar to the analog auto calibration. So going to the adjustment tab again, adjustment digital this time. We've seen this already. Here are our reference values for the alignment still stored. And if I'm clicking adjust, I'm pretty sure that those will be matched now with the static auto calibration. So let's click this. And as you can see, okay, we have used the dynamic auto calibration already for alignment, but a static auto calibration is doing exactly this, looking at the alignment between code disk and sensor and compensating for somewhat of a misalignment. So that's it for the digital auto calibration. And what we have done now are all steps that are necessary to build up an encoder system with the iC-PZ series, or in this case, the iC-PZ 205 with the 69mm disc. And let's see if we're getting a stable position signal. Therefore, first I'd like to to open the data window. For those of you who are not familiar with this, we do have a data window that is showing like a position plot over time, and yeah, I'm reading the sensor now, and let's see if we're getting a signal. Okay, so this is, I'm spinning pretty too fast now. But as you can see, this is a sawtooth. Looks good, as expected. But what is probably not expected when starting a system is that there are some errors. But what you have seen is that we have just started with a mess of alignment with the system. So I'm reading all of those errors, and they are from our previous messing around with the alignment, because all of those errors are alleged if occurred once. So I'm pretty confident, let's see, when clearing those errors, that they will all be gone. Read the status again. No errors whatsoever, so this looks absolutely beautiful. And we've just set up our rotary encoder with the iC-PZ series. And there's one last step I'd like to show here that is optional. And this is our eccentricity compensation. And as all encoder builders will be aware of, when mounting a disk on a hub or gluing a disk on a hub, there will be some radial runout error. And we can compensate of up to 95% of that error inside the chip. And therefore, we do also have a auto calibration feature on board. I'd like to show how to execute this. And then we will store the configuration inside the chip, and we're done. So again, going into the GUI, adjustment this time, the adjustment eccentricity, so the third tab in the adjustment tab. Clicking this, and I'm spinning a bit faster so we can go through this step quite quickly. Again, just sending a serial command, calculation and computation is done within the chip. So clicking this, and what the system will do now is analyzing the eccentricity, and then if I'm enabling the correction, will compensate for that long wave error over a full turn. So what you can see here are the 27 micrometer of eccentricity that the system has just calculated. And again, I can re-execute this to check if this is a stable. And I'm doing so, waiting another few seconds. Okay, so this seems very, very stable, 27 micrometers of eccentricity. And by hitting the checkbox here, enable eccentricity correction, I'm enabling this, so I'm getting a boost in accuracy. Okay, so that's it basically for all the configuration and calibration steps. And last thing you have to do is just store the configuration and all the adjustment parameters to the EEPROM. This is also done by just sending a command, and all the data handling and pushing over I2C to the EEPROM will be done by the chip. This is very handy, by the way, in the GUI, because all you need to do is going to the bottom right corner, doesn't matter in which tab you are in, and hit the right EEPROM button. So that's it. Here it's stated, I'm not sure if you can read this, but by clicking this button, the command conf write all will be executed. So it's really just a command, again, that is sent here. And to double check if the EEPROM contains your parameters, we can go to any adjustment tab. Let's stay in the eccentricity adjustment and reboot the system. We can do this by sending a command. So here it's command 10 hex, and I'm just writing this command so the system will reboot. And you're seeing all your auto calibration parameters, and other settings you have just adapted. So the system is stored inside the EEPROM. Okay. Spinning a bit slower now so you can see the sawtooth again of the position. So that's it for setting up the system in the lab. And for those of you who are already working with the iC-PZ, probably have already prototypes or are pretty serious, they will be asking, what about series production? So do I need all of those steps in series production? And the answer is clearly no, because you start with a predefined config. You do not have to go through all of those configuration steps that I've just showed. So all you're doing is loading the predefined config, executing the auto calibration features, and afterwards writing the config back to the EEPROM. So that's it. Should be very, very quick in your production. So I'm done with my hands-on presentation here, and I would again, first I would like to thank you for watching, and then I would again hand over to Goran, who will be presenting a linear stage application. And I'm asking for your understanding that we will need to switch demos here, which will take like 2 or 3 minutes, and we will send a poll out, and it would be very nice if you could take part. So thank you very much.
Hello, and this is me again, and I would like to show you now the linear stage and the linear application of iC-PZ 205. So let's start with the components that we have here on the linear stage. First, we have the same scanner module with the PZ 205. We have the motherboard PZ2D. We have the BIS to PC adapter for the communication to our GUI software. And the only difference to the setup that you have seen from Silvan is that we have now here a linear scale. This is our reference glass scale with 160 millimeter long and consists of 204.8 micron incremental pitch. So I won't repeat all these calibration steps because it's the same as you have seen for the rotary ones. So this system is already configured and adjusted. And what I like to show you now is that when I will start up the linear stage. So as you can see here, we have now certain lengths that is scanned by the PZ205. It's roughly 50 millimeter long or length. And in the data window that you have also seen from the rotary application, you can see now if we tap the reading of the sensor, now we have the absolute or the position in the Y scale. You see the digits or what we call the positions. And in the X direction, we have the time frame of the reading of the PZ205. So now we can choose here, similar to the rotary ones, that we can switch, for example, to another resolution. For example, if we use a very simple resolution. So as you can see here now, these 550 millimeter lengths of the scale is, the resolution is very poor. It's just, as you can see on the left side in the Y axis, it's just divided by 30 or 20 digits of positions. So if you use the maximum resolution, which means that we have, right, what you can see here is that every digit or position is less or down to 12.5 nanometer, because this is the maximum resolution that we can get out from the PZ205. It's 204.8 micron native divided by the 14-bit interpolation core. So to show you also, or to present you also the accuracy, the high sensitivity of the PZ, we can go to the standstill position. And as you can see now, we are almost in the noise level of the sensor itself. Of course, with some vibrations that we have from the mechanics. And for example, I can show you by tapping onto the stage of the scale or the setup, you can see that here we have some deviation and some digits in the range of micron or submicron caused by these kind of vibrations. Or, as you can see, there are also some swinging of position. So here you can see very clearly how precise or how high the resolution of the PZ205 is. So when we talk about linear applications, there is sometimes that applications are limited to the linear speed. So we have here an option, it's also mentioned by Silvan before, that in all these calibration procedures, adjustments, there is an option that's called low speed option. That means if you have, for example, a linear stage with just a few millimeters per second, you are able to also apply all the adjustment features and adjustment procedures with the PZ205. So this is just roughly the presentation of the linear stage. Everything is the same as you have seen on the rotary. All the process steps for calibration, adjustment, storing all the setups is the same. Even the hardware is the same for the sensor. So that's it from the linear stage, and I hope we have some results from a polling and questions from your side. I will hand over to Henry.
Thank you, Goran, and thank you, Silvan. Excellent presentations. Just very quickly, the polling, roughly 54% of all the answers were for both, which is good, which means that we covered for everybody. And I know we are very close to ending the session, but I do want to let you have a couple of questions. We have many questions, and please be aware of that we will answer the questions afterwards, and you will also get a recorded link of this presentation as well, so you can always ask questions to Silvan and Goran. But let me just read a couple of questions before we end the session. So the first question is, if we use a code disk of 45 millimeter, can it be applicable for both? So the PZ2656 and the PZ205, Goran?
No, we have different codes on the 45 millimeters for 2656. It's more roughly the outer diameter of 45. The code for the smaller one is a little bit smaller, and therefore for the bigger one, it's a little bit bigger. So there is no hard age, but it's more related to the outer diameter of the code disk itself.
Okay, thank you, Goran. We have time for one more. So could you inform what maximum position reading sampling frequency one can get from the IC?
When we talk about maximum frequency, basically it's limited on the front end. That means the maximum input speed is limited. That means if we talk about what we have seen, 1024 CPR on a code disk, the input frequency, maximum input frequency is 240 kilohertz. So this is the limited factor on the optical front end. Okay,
thank you, Goran. And now the last question. Does it matter what speed the eccentricity adjustment run is done? Is there a specific parameter? Goran?
I would like to pass to someone.
Yeah.
Because he showed out also the eccentricity.
Would be great. Hello again. So yeah, the eccentricity correction, you will require at least 30 RPM. So higher doesn't matter, but at least 30 RPM. And it's very necessary to rotate at constant speed. But 30 RPM is the lowest one possible. Thanks for asking.
Okay, so that concludes today's session. As I said before, your questions will be answered. And just as a final note, we look forward for you to join us on our next webinar, which will be on Tuesday, March the 23rd at the same time as today. And we look forward to hosting you again. And thank you very much for attending. Have a good day and stay healthy. Bye-bye.
Thank you. Bye-bye.
Bye-bye.